Friends, welcome. We will continue the example for the polar form. Say take z is equal to 1 plus I. Say 1 plus I, we can write it as square root of 2 into cos pi by 4 plus I sin pi by 4, where r is equal to square root of 2 and that is equal to root of 1 square plus 1 square, it is equal to root 2. Similarly, argument is equal to pi by 4. How it is? As I have explained you, argument or amplitude theta is equal to tan inverse of y by x, because both the point 1 comma 1, 1 plus I, we can write it as 1 comma 1 ordered pair of number, it lies in the first quadrant. Therefore, theta is equal to tan inverse of y is 1, x is 1, it is nothing but tan inverse of 1 and that is equal to pi by 4. Hence, 1 plus I in the polar form can be written as root 2 into cos pi by 4 plus I sin pi by 4. Third example, take minus 1 minus I. Now, observe that this number lies in the third quadrant and we can convert into polar form. Minus 1 minus I is equal to, again modulus is going to be root 2 and amplitude is going to be minus pi by 4. Hence, 1 minus 1 minus I is equal to root 2 into cos minus pi by 4 plus I sin minus pi by 4. Similarly, you try it yourself. Some more example I have given to you for your homework, and that is minus 1 minus root 3 I, you convert into polar form 2 plus 2 I and minus 2 minus I. You may try yourself some more problems. Now, the third form of complex number is exponential form of a complex number, and that we can write it as we know that z is equal to x plus iy is called Cartesian form and z is equal to r into cos theta plus I sin theta is called polar form, and the third form z is equal to r into e to the power I theta is called exponential form of complex number. Here e to the power I theta is equal to cos theta plus I sin theta, and first time it was given by famous mathematician Leonardo Euler. Now, you can take some more example. For this year it is how to convert a complex number in the exponential form. The same example you take, z is equal to say 1 plus I. Here r is equal to root 2 and theta is equal to pi by 4. Therefore, while writing 1 plus I in the exponential form, it will look like 1 plus I is equal to root 2 into e to the power I, theta is pi by 4. This is called exponential form. Therefore, in the complex number, you can write a number in 3 different forms. One is Cartesian form, another one is polar form, and another one is exponential form. You may try yourself some more example. Now, as you know that a number can be represented geometrically, real number I mean, again a complex number also we can represent geometrically, and that is here as in real numbers x axis and y axis. Here x axis is called real axis and y axis is called imaginary axis. Therefore, we can write a complex number in the complex plane. Representing a complex number in the complex plane, it is called Argand diagram. For example, you take z is equal to 2 plus 3i. We can write as 2 and 3 are real numbers, we can write 2 plus 3i as 2 comma 3. Therefore, there is a one-to-one relation between or set of complex number and the set of real numbers. Therefore, we can write 2 plus 3i as ordered pair of numbers. So, it represents a point in the real plane. Similarly, minus 1 minus 3i, it lies in the third quadrant and that as ordered pair of numbers minus 1 minus 3i, or root 3 plus I is equal to root 3 comma coefficient of I is 1, it is 1. We can write root 3 plus I is equal to root 3 comma 1. It lies in first quadrant. Similarly, minus 1 plus 1 minus root 3 I, it is represents in the fourth quadrant, that is 1 comma minus root 3. So, therefore, every complex number you can represent in the complex plane. As usual, the set of all points on the real axis is represented by x comma 0 and set of all points on the y axis, that is imaginary axis, is represented as 0 comma y. Here origin is equal to 0 plus I into 0. Now, as for your convenient purpose, I have shown a diagram corresponding to it. Just go through that. There I have represented R. R is nothing but modulus Z, as I have defined earlier. Mod Z is equal to root of x square plus y square. Continue. Now, as you have defined, these are the fundamental aspect that we have defined, different forms or different examples that I have given the basic or introduction about the complex number. Now, we will continue the topology of complex number as you have defined in set of real numbers. Now, first of all, we will define what do you mean by neighborhood of a point. Suppose if you are considering neighborhood, it is also called circular neighborhood. You take a point z0, a given point on the set of complex number. Here we will denote it as S, that by the neighborhood of a point z0, we mean set of all points lying inside the circle having z0 as center and radius is epsilon. Epsilon is a very small positive quantity, and you are using neighborhood by using epsilon, hence it is called epsilon neighborhood, and that we will write it as modulus of z minus z0 is less than epsilon. It represents a circle, and that is what epsilon neighborhood. Next, we are going to define, with the help of neighborhood, we are going to define interior point, exterior point, boundary point of a set in the next class.